Hello everyone, this is the video lecture of section 8.7 part 2. Section 8.7 is divided into 3 parts. This is second of those 3. Section 8.7 of Calculus 2, Math 2520. Okay, at the end of the first part of section 8.7, we showed that we learned Taylor's inequality, right? If your n plus first order derivative is always less than or equal to capital X, some number, for all x plus minus, within plus minus d around a, from a minus d to a plus d, then the remainder, nth remainder, that means the error when you use nth degree Taylor polynomial as approximation, and that the error of that is less than or equal to capital F, that maximum value of n plus first order derivative over n plus 1 factorial and x minus a to the n plus 1. And I told you that this is basically upper bound of the n plus first power term of the Taylor series. The first term you discarded in the approximation. It's kind of similar to alternate series estimation theorem, right? Alternate series, when you satisfy those two conditions, absolute value of a n decreasing and going to 0, then alternate series conversion. Not only that, if you use the first n terms as sum of the n terms, Sn as an approximation, then the error is bounded by, upper bound of the error will be the size of the n plus first term. The first term discarded. The first term discarded, maximum possible value. Using those, in example 2, we proved that e to the x Taylor series actually conversion to e to the x. So we finally proved that e to the x is analytic at 0. Okay, now let's continue. Example 3. Examples 3. Let's find the Maclaurin series of sine of x. Okay? And show that that Maclaurin series indeed converges to sine of x. So if you do this, f prime of x is cosine of x, right? F double prime minus sine. F third order derivative minus cosine. Fourth order derivative back to sine of x, right? So after that, the fifth order derivative will be cosine, right? Sixth order derivative is minus sine, then minus square, back to sine of x. So every fourth terms will come back to sine of x. So f of 0 equals 0, f of 0 equals 1, f prime, second prime, third order derivative, minus 1, fourth order derivative, fifth order derivative, and it's going to be 0, 1, 0, negative 1, 0, 1, 0, negative 1. Every other term is 0. The other every other terms will be alternating between 1 and negative 1. Okay? Here, in e to the x was derivative at 0, it was always 1. Here, this. So, the first thing is 0. Plug it in Taylor series formula. This is 1 times x. 0 over 2 factorial x squared minus x to the third minus 1 times x to the third over 3 factorial plus 0, and then 1 times x to the fifth over 5 factorial, and then 0, and again minus, all right? So this can be written as minus 1 to the nth, x to the nth, over 2n plus 1 runs from 1, 3, 5, so all positive integers. When n equals 0, positive, and after that, negative. Alternating sign, 2n plus 1. So you can write it this way. Now, interesting thing is that your sine x Maclaurin series is almost same as odd power terms of the exponential function. The difference is from the odd powers of the exponential function, you just take alternating sign, right? 1 plus minus plus minus plus minus. So this one has a close relationship. We're going to see that cosine also has the similar relationship later. Now how do we prove that? This is conversion. Okay. For now, we don't know the conversion. We only know that if sine of x has a power series representation, then this should be the one. Now, how do we prove that the sine of x indeed converges to this? Again, we have to use Taylor's inequality. Here, okay, wait a moment. All right. So whatever n is, n plus first order derivative will be either plus or minus sine of x, or plus minus cosine of x, right? Therefore, absolute value of this is sine x, absolute value of sine or cosine, all of them are less than or equal to 1, right? Maximum 1 for all x. So in this case, d can be any real number, any large real number for all x, because it is for all x. All right. So our capital M is actually 1. Then, according to this, what is it? Our n will be going to. Where did I show it? Oh, here. So, our n of x is less than or equal to 1 over m plus 1 factorial x to the n plus 1. Okay? Now, for all x, d can be any large number. We know that for any number x, once you fix x number, this one goes to 0. This one goes to 0 as n goes to infinity. Therefore, remainder goes to 0. Right? So, therefore, limit of Rn of x goes to 0. Okay, for all x in the real number. Okay, that's it. That's why this is indeed converted to sine of x. Okay, just like e to the x, sine of x Maclaurin series also converges to every, because this one, we knew that this one has infinity as radius of conversion. All right, and now example 4, we want to consider cosine of x sine of x. So sine of x squared. Okay, let's do b first. Okay, let's do b first. So in b, yes, you go through the same thing. You can go through the same thing. Cosine of x equal f of x is cosine, f prime is minus sine, f double prime is minus cosine. Or you can use this. Now we know that sine of x is a conversion power. Power series representation with radius of convergence r. Therefore, its derivative also has a power series representation whose power series is obtained by turn-by-turn differentiation. That was the main result from section 8.6. So you can think about this x minus x cubed 3 factorial x to the 5th. Forever. Derivative. Turn-by-turn differentiation. 1. 3x squared. 3 cancels. So minus x squared over 2 factorial. 5 cancel. X to the 4th over 4 factorial. 7 cancel. X to the 6 over 6 factorial. So you can write it as 0 to infinity minus 1 to the nth over, okay, you can write it, and this is true, this is conversion to cosine of x for all x, because we already knew that sine of x has a power series representation, so does cosine of x. Alright, you just take the derivative, 2n plus 1 terms cancel, so actually 2n, x 2n factorial, so. Okay, now a. Now for a, think about a. Now you could do this. Now Taylor series formula, Maclaurin series or Taylor series formula. Maclaurin series. Nth order derivative of 0 n factorial x to the n. This is elegant and very easy to remember. But when you try to use this Taylor series formula here, then you have to do what? 2x. You have to use chain rule. Second order derivative, now you have to use product rule. F prime g plus fg prime. G prime will give you minus, okay, minus sine of x squared times 2x. So 2 cosine of x squared minus 4x squared sine of x squared. Now think about third derivative. Minus 2 4x sine of x squared. And then you have to do what? 8x sine of x squared minus 2x comes 8x cubed cosine of x cubed. So you have to combine. So it's getting more and more positive. So it would be very hard to see the pattern, even if there is. Alright? Of course, f of 0 equals 0. F prime of 0 is also 0. So if you want, you can write minus 12x sine of minus 8x. Alright? And this one, f prime of 0 equals 2. So, it would be very hard to see the pattern. So, despite this elegance of the formula of Taylor series, unless you have a way to find the formula of f nth order derivative is 0, it would be very hard to use explicitly, right? So, other approach would be this. Now, we already learned this, sine of x, other approaches. We know that this has a power series representation already. 2n plus 1. Therefore, this is for every x. Well, why don't we just replace x with x squared? Alright? Then that would be 2n plus 1 factorial factorial minus 1 to the n, x squared, 2n plus 1. Alright? So, sine of x squared will be minus 1 to the n minus 1 to the n power x to the 4n plus 2 over. Okay, it's much better to have a composite function. Substitution x squared for x in the already known Taylor series. Okay, so this is very, very useful techniques. So, a few terms. Instead of x squared minus x to the 6, and then x to the 10th, x to the 14th, every fourth power. Okay? This is for all x in the real number. We knew that this one is conversion for all x, therefore this is also conversion for all x. Okay? Alright, next one. Example 5. A. Find the Maclaurin series of e to the negative x. Again, we can use Maclaurin series e to the x. E to the minus x squared. So, instead of x, we have minus x squared to the nth power over n factorial, right? Instead of x, we put minus x squared. So, we can rewrite it. Minus 1 to the n, x to the 2n over n factorial. Okay? For all x in R. Then would be minus x squared. Minus x squared. X to the 4th. Okay. Keep going. B. Evaluate indefinite integral. When you have a power series representation, this indefinite integral can be obtained by taking term by term integration. Right? Integrate this one. We need 2n plus 1 here. Minus 1 to the nth, x to the 2n plus 1. Okay? Term by arbitrary constants. And if you want, you can rewrite it. Integrate x minus x to the 3rd over 3. X to the 5th over 5 times 2. I'm going to just keep it. 7. 9. 10. 11. That will be the first few terms. Indefinite integral. Obviously for all x. Okay, for all x in the real number system. Now, C. Definite integral. Definite integral is this one. Zero to 1, right? This one is 0 to 1. So it's going to be 1 minus 1. The x equals 1. So this x all will be replaced by 1. 1 over 2 times 5 times 2 minus minus 1 over 7 times 3 factorial. One over 11 times 5 factorial. So obviously this is alternating series. Okay? But if you want, you can write it as over here. Minus 1 to the n over 2n plus 1 n factorial. So this is your an. Absolute value of an is 1 over 2n plus 1 n factorial. Obviously this one is decreasing and converges to 0. So not only this is convergent, alternating series, is approximation by SM. No matter where you stop as approximate value, its error will be less than or equal to the next term. The first term you discarded. Now, I asked you to find the correct within the error of 1 over 1000. So if I stop here, then error will be less than or equal to this. This is 24 times 9. Well, this is not less than 1000. This one does. Because 5 factorial is 120 times 11. 1320. So we have to use this as our approximate value. Okay? If you calculate this, so this one is approximated by this value, which is point. This is exactly. If you keep going, then exact value. This is 0.7475. This is with error is less than or equal to the size of the first term discarded. 1 over 11 times 5 factorial. 1320. Definitely less than 1 over 1000. 0.001. So this approximate value is accurate up to within an error of 10 to the negative third power. Okay? Alright. Next. Evaluate. I forgot to mention this. Your sine of x, look at this. Your cosine, we learned cosine here, right? Cosine of x equals, I'm going to just write it here. Minus and sine of x okay. So these are the power series you must memorize. And Maclaurin series ETS is very easy, right? This is the most well-known, easiest to remember. If you remember e to the x power series representation, then power series of cosine x or Maclaurin series cosine x sine of x are taking only odd even power terms or odd power terms in alternating signs. Okay? If you have to add one more power series, you must remember to do this. 1 plus x equals actually over n x 0. I think this one is plus or not. I think it is just a plus. Let's see. Where's the power series? I think we already did that. Yeah, this one is alternating square. Now I have to have minus 1 to the n plus 1 x to the n over n, not n factorial, n. Okay? We learned this one in section 8.5. Okay? Alright, those 4 power series you might want to memorize. Let's do evaluate limit of sine of x over x. Example 6. Now, we learned this limit in calculus 1 using squeeze theorem. You were able to get this was 1, this value 1. Let's take another approach using Taylor series, power series representation. Now, sine of x, again, as you can see, equals x minus x cubed over 3 factorial. This is true for all of x, right? Now, take out x. You can write it. Therefore, sine of x over x will be same as this power series representation. For all x other than 0, because we divide both sides by x. Okay? Now let me check recording. I thought that I forgot to push button. I did. Okay. Then, now this is true for all x. So when you take the limit, not going to 0, but going to 0. In the limit process, your x is only getting close to 0, but never ever be exactly 0. So only close to 0, but not 0. Therefore, no, this is same as this. Now, think about it. If you forget about sine of x over x, if you think about only this power series, using ratio test, you can show that this is convergent everywhere for with radius of convergence infinity. So if you say that this is function f of x, right? This is power series representation of some function whose radius of convergence infinity. And any function which has a power series is differentiable everywhere, therefore continuous. Because it is continuous function, limit value is exactly same as function value there. Plug in x equals 0, will be just 1. Okay? So, let's say this is f of x. Your f of x, a function this one is representing for all real number x, is same as sine of x over x, as long as x is not 0. When x equals 0, this value will be 1. So, this is that power, so your f of x is actually this. So this one cannot define value as 0. At 0, we define separate piecewise. And this is the power series representation of this f of x. Okay? All right. Okay, now example 7. A. Find the first three non-zero. Now here, let's say, if you take page 10, the second method is the usual one. F of x equals e to the x sine of x. You know, if you want to use Maclaurin series to get the first few non-zero terms, you have to go through this, right? Product rule. And then another product rule. So this is e to the x 2 cosine x. So this is getting complicated, right? It's hard to see. It's hard to see the pattern also. All right. So yes, you can do that third derivative, e to the 2x cosine of x minus 2e to the x sine of x. So f prime of 0 equals 0, 1, f double prime 0 is 2, right? F triple prime of 0 is also 2. See? It's hard to see the pattern. But anyway, if that is the case, e to the x sine of x is f of 0 equals 0 and then 1x and then plus 2 over 2 factorial x squared and then 2 over 3 factorial. So 2 over 6, 1/3 x to the third and keep going. Alright? So you can get this one. You can do it that way. That's the second method of your lecture notes. Another method, which can be done quite efficiently if you have enough experience. Another method is e to the x sine of x. Because these are very famous functions, I know that first few terms already. 3 factor is 6. This times x minus x cubed over 3 factor is 6. 5 factor 120. I don't need it because I want to get here the first three non-zero terms of the Maclaurin series. That means up to x squared if every term is non-zero. Alright? So I don't need this actually. And then think about what? Distributing. Alright? We did this one in section 8.5. When you have a two convergent power series, and then the product of those power series representation can be obtained by infinite Feynman. X times this. X plus this one times minus x cubed over 6. Alright? And keep going. Same thing will be, what was it? 120. So, I just need the lower power terms. X plus x squared plus x to the third over 2 from here minus x to the third over 6 and then higher order term, I don't care. Alright? So from there, this one from the beginning, x to the fifth over 120 something. Alright? So in the end, x squared 1/2 minus 1 over 6 is 1/3. Now, I showed every single step. But then an experienced person, when they see this, they instantly recognize this one as x squared, 1/2 x cubed, and then minus 1/6 x cubed. And that's it. And then we also know that there's 0 x to the 4th term. Okay? Because next term, the smallest one. Ah, 4th term is over here, I'm sorry, minus 6. Minus 1/6 x to the 4th. That's the only term there. Alright? So even for up to 4th power, you can get this one pretty quickly, actually faster than when you do this. So sometimes infinite folding is convenient if you have experience and practice. Okay? Alright. That was e to the x. And let's do, last one was tangent of x. Let's say b. Tangent of x. Again, you can do this one. Tangent x, f prime of x is secant squared of x. Okay, 2 secant of x times derivative inside secant tangent. Now you can, as you can see, it's getting complicated, right? So, yes, you can do it just Maclaurin series formula, or you can do it as a long division. 3 factor is 6 over 5 factor 120. Okay? You can do it this way. Minus divided by 1 minus x squared over 2 plus x to the 4th over 4 factor 24. Okay? So let's do long division. Now, in power series long division, we start from constant. Constant term is the most important one, and then x and x squared, x to the 3rd. Unlike long division of polynomial, in that case, from the highest power, right? The highest. Here, so if you do this, divide this one by 1 minus x squared over 2. First of all, we need x, isn't it? X times this. Subtract. You subtract. Positive 1/2 minus 1/6 is 1/3 x cubed. See? 120 minus 1/24. 5 over 120. So minus 4 over 120 means minus 1/30. Right? Minus 1/30. And then for this one, what do you need? For this, 1/3 x cubed, right? 1/3 x cubed multiply minus 1/6 x to the 5th, whatever. Now subtract. Positive 1/6 minus 1/30. So this is 5/30 minus 1/30, 4/30, 2/15. Whatever. So then I know that this one has to be 2/15 x to the 5th. And I don't care about the next one. Okay? Because they asked you to find the first three terms. X minus 1/3 x to the 3rd, 2/15 x to the 5th. Okay, the first three terms here. As you expected, tangent x is a function we already know. That's why tangent x also includes only a power term, just like sine, a power term. Even function cosine, even power terms. All right. So, long division of power series can be done. It can be useful in some cases. All right, so that's the end of second part of section 8.7. So, next time we will cover the third part of section 8.7. That concludes section 8.7, and that is the end of the course, Calculus 2. All right, so just one more video lecture for the course Calculus 2. All right, I'll see you next time.